Welcome back to Tech Tangents, everyone. I'm Jenny.
And I'm Mark. Ready to dive into something? Well, foundational today, Jenny?
Always. What cornerstone of computing are we examining this time? Please don't say it's the humble power button again, Mark. We did that.
Chuckles. Tempting, but no close though, in a way. We're talking about memory, specifically computer memory, and how a really key type, SRAM, seems to be encountering some significant hurdles.
SRAM. Okay, static RAM. That's the really speedy stuff, right? The memory that lives right times on time the processor chip itself, working as cache?
Exactly. It's been the quiet workhorse for decades, the CPU's super-fast scratchpad, letting it grab data in mere nanoseconds. Without it, everything slows to a crawl. But the long-standing trend of making SRAM cells smaller and packing them tighter with each new generation of chip manufacturing? Whoa! Well, that progress is slowing down considerably.
Hitting hurdles? That sounds important. Is this another case of Moore's Law getting tired, but specifically for memory?
It has a similar feel, yeah? We're running into fundamental physics. The transistors that make up each SRAM memory cell are now so incredibly small, we're talking feature sizes dipping below 20 nanometers, that minuscule variations during manufacturing start to cause major headaches, and engineers call it transistor variability.
Okay, variability. So when you're working at that scale, it's like, not all the microscopic components come out exactly identical, like tiny imperfections?
Precisely. Imagine trying to build with Lego bricks the size of molecules, and some are just fractions of a millimeter off. At this scale, those tiny differences in transistor properties mean the memory cells might struggle to reliably hold their state, the 0 or the 1s. Especially because modern chips run at very low voltages to conserve energy, making the circuits more sensitive.
And that sensitivity leads to errors?
Exactly. Data corruption. Which is, generally frowned upon in computing. The laughs. So, manufacturers can't push the size down quite as aggressively anymore without risking instability.
Right. Instability is bad. So what's the consequence? Do they just stop shrinking the SRAM portion of the chip?
Effectively, yes. The scaling, the shrinking, slows dramatically for SRAM compared to logic transistors. I saw some research data, for example, pointing out that TSMC's N3E node, that's a very advanced manufacturing process, showed almost no times improvement in SRAM density compared to their previous N5 node. 0% improvement in how tightly they could pack the memory cells.
Hang on, 0? Not just slower, but a dead stop for that specific generation? Wow. Okay, that really changes the equation for chip designers, doesn't it? If you can't cram more cache into the same area,
it forces difficult decisions. Option 1. Make the overall chip physically larger to fit the desired amount of cache. But bigger chips mean fewer chips per silicon wafer, which increases the cost per chip significantly. Option 2. Dedicate a larger percentage of the chip's precious real estate just to SRAM.
And if you do that, you have less space for the actual processing cores or the graphics units or specialized AI accelerators, right?
Correct. I read somewhere, and you might have seen this too, Jenny, that some modern high-performance CPUs and GPUs already dedicate 30%, sometimes even more, of their die area solely to SRAM cache. That's a huge chunk.
30% just for the fast scratch pad. It really highlights how critical that cache speed is, but also what a bottleneck the density issue is becoming. So the industry must be exploring workarounds, right? Alternatives?
Oh, absolutely. The engineering creativity kicks into high gear when faced with a wall like this. One major direction is architectural innovation, thinking differently about chip construction.
You mean like changing the chip layout? We've talked about multi-chiplet designs before. Is that relevant here?
Spot on. Instead of designing one massive, complex chip, a monolithic design, companies are increasingly building systems using multiple, smaller, specialized chiplets connected together. AMD's 3D V-cache technology is a perfect example applied to this memory problem.
Ah, right. They stack a dedicated cache chiplet directly on top of the main processor chiplet, correct?
They do. It's a clever bit of vertical integration. They essentially add a large block of L3 cache using a DRAM-based chiplet, connecting it with very high-density vertical connections. This provides a massive boost in cache capacity without eating up more area times the primary CPU chiplet.
That sounds technically complex, but strategically smart. Get more cache close by, even if it's not quite times as fast as the on-die SRAM. But does that off-chip hop, even if it's tiny, introduce any delays? Any drawbacks?
That's a key point, and a potential counterargument. Some experts, like Steve Wu from Rambus, emphasize that moving data off the primary die, even to a closely stacked chiplet, always introduces some amount of latency. A tiny delay. For many tasks, like gaming, where 3D Vcache shines, the benefit of the huge capacity outweighs the small latency penalty. But for applications that are extremely sensitive to latency, it might not be the ideal solution.
So it's a trade-off. Extra capacity versus a slight speed hit for accessing that extra capacity. Okay, so chip stacking is one path. What about changing the memory technology itself? You mentioned alternatives earlier.
Right, that's the other major avenue of exploration. Looking beyond traditional 6-transistor SRAM cells, engineers are investigating, and in some cases reviving, other types of memory. One candidate is eDRAM, embedded DRAM.
Embedded DRAM. Like the main RAM in our computers, but built onto the processor package?
Sort of. It uses a different cell structure, typically one transistor and one capacitor, which makes it much denser than SRAM. You can fit more megabytes in the same physical area. The catch is, like regular DRAM, it's dynamic. The capacitor leaks charge, so the data needs to be periodically refreshed, which consumes a bit of power and adds complexity.
Ah, the leaky bucket analogy. So denser, potentially cheaper per bit, but needs that constant topping up. Another trade-off. Space versus power/complexity.
You got it. And then there's a more exotic option gaining traction in research. FeRAM. Ferroelectric RAM.
FeRAM? Ferroelectric. Sounds magnetic?
Not quite magnetic. It uses a ferroelectric material whose polarization state can be switched with an electric field to store a 0 or 1. The really interesting property here is that it's non-volatile.
Non-volatile? You mean like SSDs or flash drives? It holds onto its data even when the power is off?
Yes, but potentially much faster than flash, with endurance closer to DRAM or SRAM, and it operates at very low power. The challenges have been density and manufacturing cost. Integrating these unique materials smoothly into the standard chip-making process is tricky.
So potentially fast, low power, and persistent memory. That could be useful for specific things, maybe devices that need to wake up instantly or operate on very little power?
Exactly. Think Internet of Things sensors, edge computing devices, maybe certain types of accelerators. It might not replace all SRAM, but it could carve out important niches.
It feels like there's a real strategic debate shaping up then. Do you focus engineering effort on clever architectural solutions like stacking chiplets, which uses existing, well-understood memory tech? Or do you invest heavily in maturing these alternative memory types like eDRAM or FeRAM, hoping for a breakthrough in density or cost?
That's precisely the conversation happening across the industry. As we mentioned, folks like Steve Wu argue that keeping memory as close as possible, ideally on the same die, minimizes latency. So improving on-die memory density, even if it requires new materials or structures, remains highly desirable.
But then you hit the manufacturing wall again. Which is ultimately harder, Mark, integrating chiplets reliably in 3D stacks? Or introducing completely new ferroelectric materials into a fabrication process that costs billions and is tuned for silicon?
That is the multi-billion-dollar question. Times laughs. Integrating new materials into high-volume manufacturing is notoriously difficult and expensive. We saw this with Intel's Optane technology. Interesting properties, based on phase change memory, but the manufacturing cost and integration challenges ultimately limited its success in the market.
Right. A cautionary tale. So maybe the multi-chiplet approach, working with known silicon processes, is the more pragmatic path for widespread adoption in the near term, even with that small latency trade-off?
It certainly seems to be the dominant commercial trend right now for high-performance parts. But, and this is important, research hasn't given up on making SRAM itself denser. They're working on entirely new transistor-time structures.
New transistor structures? Beyond the thin FETs we have now?
Yep, things like gate-all-around, GAA, transistors are coming online now. And beyond that, research labs like IMEC in Belgium are pioneering concepts like forksheet transistors.
Forksheet? Okay, you have to explain that one. It sounds like something you'd find in a kitchen drawer next to the cookie sheet.
Chuckles. It does, doesn't it? The basic idea is to find ways to place the N-type and P-type transistors, the two fundamental building blocks of standard CMOS logic and SRAM cells, even closer together. Forksheet introduces a dielectric wall between them, allowing them to be packed more tightly side by side. Sort of like, well, tines of a fork, maybe?
Okay, packing transistors closer vertically or side by side using new insulating tricks. And the benefit is
higher density IMEC projects that forksheets and related concepts like complementary FETs or CFETs, which stack N and P transistors vertically, could allow SRAM cell sizes to start shrinking significantly again, maybe pushing densities towards 50 or 60 megabits per square millimeter in future process nodes.
Whoa, okay, so maybe the reports of SRAM scaling's death were exaggerated? It's just shape-shifting into forks and stacks?
Potentially. It could give traditional SRAM scaling a renewed path forward for a few more generations. But, and there's always a but at this bleeding edge, these new transistor structures are also extraordinarily complex and expensive to manufacture reliably at scale.
It always circles back to manufacturing feasibility and cost, doesn't it? If these advanced chips using forksheets or 3D stacking or exotic FeRAM become wildly expensive, does that mean progress at the top end doesn't trickle down as quickly? Could high-performance computing become less accessible?
That's a very real concern. Leading-edge chip manufacturing, the fabs that build these things, already cost tens of billions of dollars. Adding more complex steps, new materials, intricate stacking processes. It rarely makes things cheaper, at least not initially. There's a risk of widening the gap between the highest-end processors and more mainstream devices.
And we haven't even touched much on the environmental angle. More complex processes, potentially involving new or rare materials. Does that mean a bigger footprint in terms of energy, water usage, and waste?
That's another critical consideration. Manufacturing semiconductors is already resource-intensive. While some new memory tech like FeRAM might promise lower operational times power, the times manufacturing times impact of developing and scaling up these new processes needs careful assessment. Those lifecycle analyses are crucial, but often lag behind the initial technological excitement.
It adds another layer of complexity to that debate we were having. It's not just speed versus density versus cost, but also manufacturability and sustainability. Okay, so bringing it all together. Mark, what's your prediction? Where are we heading in the next 5-10 years? Will one approach win, or are we looking at a more diverse memory landscape?
My gut feeling? Hybrid solutions will dominate. I don't think there's a single silver bullet here. I expect we'll see systems architects mixing and matching memory types more than ever before. Maybe you'll have incredibly fast L1 cache using scaled SRAM built with these new forksheet or CFET transistors sitting right next to the cores.
Okay, the speediest stuff closest to the action.
Right. Then perhaps larger L3 cache implemented using dense eDRAM on the same package, or maybe a stacked DRAM chiplet like 3DV cache for even more capacity, and perhaps specific accelerators or low-power chips, incorporating FeRAM for its persistence and efficiency.
So the memory hierarchy becomes even more tiered and specialized, tailoring the memory technology to the specific needs of that level of the hierarchy, or even specific tasks.
Exactly. It's all about optimizing that complex equation: speed, density, power consumption, persistence, and cost. Why use leaky, power-hungry SRAM for data that's accessed infrequently? It pushes designers to be smarter about data placement and movement.
It even makes you wonder if software needs to become more aware of this diverse memory hardware landscape to really take advantage of it.
That's an excellent point. Software optimization, memory allocators, operating system schedulers. They might need to evolve to understand these different memory characteristics to achieve peak performance and efficiency.
Fascinating. It shows how a challenge in one area, hitting a scaling wall for SRAM, really spurs innovation across the board. In materials science with new transistors and materials, in chip architecture with stacking and chiplets, in manufacturing processes, and potentially even in software design.
Isn't it just? It turns a potential roadblock into a massive engineering puzzle, pushing the boundaries in multiple directions. So, the supposed death of SRAM scaling might be better termed the reinvention of computer memory systems.
I like that framing. Reinvention. So the key takeaway for our listeners is that while simply shrinking traditional SRAM is getting tough, the innovation engine is firing on all cylinders. We're seeing clever architectural workarounds like chiplets, serious exploration of alternative memories like eDRAM and FeRAM, and even fundamental R&D pushing transistor tech itself with structures like forksheets.
You nailed it. The future of memory isn't necessarily just smaller SRAM. It's likely to be a richer, more diverse ecosystem tailored to different needs. And honestly, that's probably a lot more interesting to watch unfold than just tracking nanometer shrinks year after year.
It makes you wonder what listeners think is the most promising path forward. Maybe we should ask them sometime. Are they betting on stacked designs, new memory types, or these advanced transistor structures?
Good idea. And the other big question, the one everyone feels eventually. How will all this complexity impact the price tags on our gadgets down the line?
Definitely food for thought. Well, this was way more intricate than the power button. Thanks for navigating us through the memory maze, Mark.
Anytime, Jenny. It's complex but crucial stuff. Makes you appreciate the immense engineering packed into every device we use.
It certainly does. All right, that's all the time we have for this episode of Tech Tangents. Join us next time as we untangle another thread in the world of technology.
See you then, everyone.